I guess it's time to start the section. Hi everyone, I am Phil Wang. Topic of this section is v8-A neon optimization with Ne10 FFT optimization as an example. I'm going to start with some quick questions. How many people here have used neon before? Oh, surprise! It's really good actually. And how many have used neon intrinsic instead of assembly? Oh. Are you from the compiler team? Oh, great. And how much improvement do you expect from neon optimization?
400%.
What?
400%.
400%. Wow. Okay, let's start. Here is the agenda of this section. Firstly, benchmark data of v8-A with or without neon optimization are presented. From this benchmark, we can understand the value of Ne10 of neon optimization. Secondly, we will have a look at workflow of Ne10's neon optimization. Generally, we locate the hotspot and neonize the hotspot. If the hotspot is not friendly for neon, we adjust the algorithm. Thirdly, we will share some useful tips during neon optimization. Examples of Ne10 FFT and Android libraries are included. And then we'll talk about performance comparison between assembly and intrinsic. It is often the case maintainers of open source software have to choose between assembly and intrinsic. We hope our experience may help them to make this decision. Last but not the least, we would like to share our idea about less libraries to neon optimized. Neon is general purpose SIMD engine. It can accelerate multimedia and signal process algorithm. Figure here is performance ratio of FFT. Horizontal axis is length of FFT from 32 to 4096. The vertical axis here is the performance ratio of neon to C. For an example, the red bar here is 1.70, and it means the neonized, the code after neon optimization is 70% faster than the pure C version. And the higher means the neon code is faster. The red bar here is these performance ratios of ARC32, and the blue bar here is of ARC64. You can see from this figure, we can gain a performance boost from 70% to more than 100% by neon optimizing for both ARC32 and ARC64 mode. Have any question about this figure?
Yeah, when you say QoC, you mean there is no neon intrinsic?
Yes.
No vector.
Yes, no vectorization. Oh, and we disable, we do not turn on the G-vectorization flags and something like this. So we are sure the code does not contain the vectorized. But however, you know, in ARC64, we do the floating point arithmetic in neon register, so there is still some neon instructions there, but not vectorized.
Question
So when you compare it with the C, is it like KISS FFT or some library, standard library that you're comparing this against? Or is it the Ne10 implementation of C?
Oh yes, the Ne10 implementation of C.
And do the numbers compare allocation time as well for the twiddles, or is it just the processing that when you do the comparison?
I'm sorry?
You know, when you have to do an FFT, it's just not one single function call, it's actually 2 function calls or something like that, where you first have to allocate the twiddles, pre-allocate the twiddles, and then you do the FFT, right?
Only the FFT routine, the alloc and free, maybe this drive function are not included.
Okay.
Because we always alloc for once, and we can perform the FFT for many times. Now we talk about how we gain this performance boost step by step. The pseudocode from complex FFT is shown on the right side. Complex FFT contains nested loops of 3 layers and may contain a bit reorder routine. There are 2 major steps of our optimization. The first, we neonize the most inner loop. The second, we find the hotspot in bit reorder routine and discover it is not friendly to neon. So we adjust our algorithm to make it more friendly to neon. Here is the home page of Ne10. You can clone all our code from there. Here is the first step of our neon optimization. On the right, there is a figure illustrating one of the subroutines of an complex FFT. And the left here, the left figure is the normal way we do the FFT, and the right figure is the neonized way. The arrays here, means addition or subtraction. We can see from the right sub-figure that the arrays are parallel, and so we can neon optimize these operations. We can node these four element at a time, and we do the parallelized operation, and then restore them. By this neonization, we got 20% performance improvement. Any question? Is it clear? In the normal way, we take the zeros element, the fourth element, and we add them to 0, subtract them to 4. And we find out that we are doing these parallelized operations, so we collect them together, like 4, 1, 4, 0, 1, 2, 3 together. We load them together. We do the same operation together. That's so simple. Okay. And then we will find that the bit reorder is not friendly to neon. Oh, sorry. Here is the bit reorder. In bit reorder, we made take the zeroth element and store it to the 0 elements. And we take the first element and put it to the 4th slot. And take the third element to the 6th slot. So there is no way we can neon optimize this piece, right? So we adjust our algorithm. In the old algorithm, we take the element from maybe 0 to 4, and after the operation, we store them to 0 to 0 and from 0 to 4. But now we separate the bit reorder. We store them to the well-designed position, like 0, 2, 4, and 6. Then we do the bit reorder during each loop, so we don't need a separate bit reorder, which is really bad, really not friendly to Neon. Our FFT function got another 20% to 30% performance improved from this operation step. And combined with the previous optimization, we achieved the significant performance boost in the previous slides. Am I clear? Any problem about this algorithm adjustment? Okay. Now, during Neon optimization, as shown in the previous slides, we have been surprised for a few times. Now, I would like to share 3 useful tips for Neon intrinsic with examples from Ne10 and Android libraries. The first one is beware of the number of registers during Neonization. The second one is compiler flags for floating point arithmetic. And the last one is we get high penalty on ARC64. Here, on the right is a C snippet using 20 float 32 scalars. It's really small, but I'm sure that there is 2 at least scalars are using. And to neonize this snippet, we can perform 2 of it at a time, or we can perform 4 of it at a time. The former one will require, If we perform 2 of them at a time, it requires 20 64-bit Neon register. And if we perform 4 of them at a time, we will use 20 128-bit Neon register at a time. And on ARM v8-A, v7-A, or ARC32, this will result in register spill, and the performance will not be good. On the contrary, we can say there are more 128-bit Neon register on ARM v8-A, ARC64. So we can perform better neonizations before we hit the limit of Neon registers.
Excuse me, can you go back to the slide? So, one of the reasons why I use intrinsics is because I don't have to worry about the register allocation. Now, one point to note over here is that you're saying you have to be aware of the architecture you're running so that you don't use like more than 16 Neon registers, right? 128-bit registers, right?
Yes.
So then I always have to code to the common denominator, right? My advantage of Neon intrinsics for ARM v7 versus ARM v8, to stay compatible, I always have to see the limitation of ARM v7 first to make it. So is there a better way of doing that? Can I get hints from the compiler saying that, hey, you're probably using more registers than you should. It'll impact you on ARM v8. Is there a clue to give? Anyone? No.
Right? I'm sorry, I didn't get it.
So there's nothing the compiler can. I don't think there's anything the GCC certainly can't tell you at the moment to tell you that you're using too many registers. Something to think about, though.
So yeah, definitely, at least GCC will not complain, but there are precedents like vectorizer optimization in GCC that it will, if you give GCC a special option and ask it to be verbose, it will print out hints or notes that I could not do this and I couldn't do that because of this or that. And in theory, a register allocator could be improved to print out similar diagnostics.
Does it answer your question? Okay. Our last tip is compiler flags for floating point arithmetic. As you know, ARC64 has IEEE 754 compliant floating point unit. So we can use intrinsic function like this v8-Q15-408 to generate the neon assembly we want. Or actually, we can call operator add here for ARC64. The latter one is not recommended because it will result in ugly performance for ARC32 unless this option is specific. I'm sorry, is there any guys from compiler can explain this, why it is required?
GCC and LLVM alike will automatically perform folding, which is an optimization on things like constants and other variables inside the compiler. And if it takes, and by default, without the unsafe method optimization, it promises to the programmer who compiles the program that all of the optimizations inside the compiler will be followed to the IEEE specification. Mm-hmm. And on ARMv7, because the CPU cannot guarantee strict compliance with the specification, it doesn't do them by default.
I'm sorry, another question. Is this usage portable across compiler, or because it's not in the standard?
Vector add. You mean vectorize, so addition or other arithmetic operations on vector instructions?
Yes.
I think it is.
Not every implementation of Neon Intrinsic supports the use of the plus operator. So to be fully portable, you do need to use the Neon v8 intrinsic.
So yes, that is why it is not recommended. And now is the
that was just that.
Oh, can you use the microphone so that we can all understand?
The comment was that at what point you define portability. you can use ARM Neon intrinsics, and your code will be portable between various ARM compilers, like LLVM, GC, ARM's compiler, but it will not be portable to other architectures. But the point here is that if you are doing this kind of very target-specific low-level optimizations, you already know what you are going to be running on.
Thank you. Okay, the last tips is we get high parity on ARC64. Neon register layout is changed in ARC v8-A. You can see on ARC32, the register is overlapped, and the Q0 register is a combination of D0 and D1. So the higher half of Q0 is D1. But on ARC64, they are not overlapped. D1 is the lower half of V1. So intrinsic we get high is not free anymore because we have to move the higher half to another register before we can use it as an operand. Like here, we use this v8, and we add the higher half and the lower half of the A. On ARC32, we'll generate one instructions. And on ARC64, there is an actual move here. Any idea from the compiler guide that we can remove this or we can optimize this?
From what I understand, no. A question to the ARM developers, ARM core developers. Does it result in worse performance or move just discarded by the core?
Go back? Oh, sorry.
So my comment is that moves, especially register moves, are quite often forwarded inside the core so that there is no actual performance impact on the speed of whether the move is there or not. I do not know whether that is true for Neon registers or not.
You mean in code is really cheap to move this register?
That is a question I do not know answer to.
Okay. So you may use we get high and we get node in ARM v7 for free, but on ARM v8 it's not free anymore. So this may impact on the register, no, on algorithm. You may have to adjust your algorithm for this. Sorry. Now comes to performance comparison between Asambric and intrinsic. On one platform, the performance of Neon Asambric is only decided by the implementation and has nothing to do with the compiler. The benefit is that you can predict and control the performance of program when you hand-tune the codes, and there isn't surprised. On the contrary, Neon intrinsic depends heavily on compiler, and but we can program once and run on different ISAs. The compiler may also grant performance fine-tuning for different microarchitecture, and it is similar to C code and is easier to write or to read or write. Sometimes the intrinsic might bring better performance than Asambric. This is very rare, but it do occur. Let's see. This is the libraries in project in Android, and some of them use intrinsic like WebRTC, libvpx, WebP, and some of them use assembly like libyuv, libJPAC Turbo. I guess it depends on the usage, the user case. Do you have any idea why they choose intrinsic or assembly? Any? Nope.
I know why I do it.
I'm sorry, which library are you in? Or
No. So I had the pleasure of doing a Ne10 optimized ISP for a camera chip, and I started using the intrinsics.
Intrinsic.
And it was a pain because I knew what kind of code I wanted in the end. So I kept moving intrinsics around, changing the implementation until I got something I could read. But the code never looks like what you expect.
Which version of the compiler was it?
I started with the standard Android one, then I changed to 5.0 because it kind of helped a bit, but the GCC intrinsics are packaged pretty heavily with all kinds of, it's inline functions, so it's really hard for GCC to get rid of all the local temporary variables that it uses to pass parameters.
Working on it, so the nice thing about using intrinsics is that newer versions of the compiler will generate better code for Ne10 intrinsics. Matt? So yes, we know that some previous versions of the compilers generated quite a bit of extra fluff for the intrinsic code, and
So very shortly, so what I saw that, well, I took the intrinsic output and thought I could make it better, so I optimized it so to make it what I wanted. And then I saw that performance was actually worse for the handwritten code that didn't have all the extra instructions than what the compiler had done. Because when you write code in hand, you tend to group logical things together, and that's not the most optimal thing, right? Because of data dependency.
yes, and the compiler has information for scheduling instructions that are generated by the intrinsics, so that it will appropriately try to make sure that the core doesn't stall and there are no pipeline bubbles when compiling from the intrinsics code. It cannot do that for assembly code.
Yes. Actually, you know, I'm working in a Ne10 project, and in my experience, intrinsic is pretty good, and I'll show you here. Here is a Ne10 FFT on Juno Cortex A53 ARC64 mode. The time cost, the vertical axis is the time cost in seconds, and so if it's slower, it means the code is faster. The red code here, the red bar here is the Ne10 assembly, and the blue code here, the blue bar here is the Ne10 intrinsic. At some point, with aggressive compiler optimization, we can have better performance in intrinsic.
So do you have estimates on how much more or less effort it is to develop in assembly versus intrinsics?
I'm sorry, can you repeat?
So in here, you provide the final performance numbers,
Mhm.
but how does that compare to the days of developers spent on writing assembly code and spent on writing intrinsics code?
I'm sorry, I don't have this data.
It took me 10% of the time to implement the same kind of use case using intrinsics. I mean, it was just much simpler because I didn't have to think about what registers I had to manually allocate. And one point that I really like that I would agree with is when you're writing assembly, your mind is trying to put logical things together, right? But underlying the scheduling, I think, is a really big part of it because only when you do the, when you select a particular architecture, the compiler knows better. So I really like using intrinsics better than, I actually saved at least 90% of the time without having to think about which registers to use, just for that one, right?
So I had the opposite problem because I was pretty load limited. So I had to know which register was coming from the frame buffer or from in the biomatrix and which ones were going out in the end. So I had to in the intrinsics in GCC I had to pin the registers so that I knew which ones would end up in so that they could be stored together, and that was what caused all the time, I guess, getting good load store behavior. But yeah.
Okay.
Can I just make a comment that if you find anything where intrinsics are performing worse than assembly, please do report it on the GCC Bugzillas, because I consider it, and the ARM compiler team, so GCC or LLVM Bugzillas, consider intrinsics to be the way ahead, and we'd much rather use intrinsics rather than assembly. So if you're finding performance issues or code generation issues, we will look at it if you put bug reports upstream.
I actually have really, really good. I'm very happy with GCC's vectorizer. That was why I was a bit surprised before that somebody said that you should not use the standard vectorizer. It takes a bit more time to write the loops, but things just work better.
So I think the example before was using the vector types and vector addition rather than using the vectorizer per se. And yeah.
So I haven't actually used the vectorizer option for GCC and changed my C loop. Is there like a suggestion on these kind of loops? It's probably just better to use like intrinsics, like for example, FFT kind of use cases. But is there like a recommendation on these kind of loops? You would probably better off just using a C code and then use -F3 vectorize option.
To put in a shameless plug, this is probably a good topic for Next Connect's advanced toolchain usage topic.
Okay. Now we comes to an open discussion. We want to talk about Lex libraries that works Neon optimization. Recently, we have optimized, Opus has been neonized, and according to the performance profiling data, it can be at least 10% faster if only the FFT routine is neon optimized. And so I'm pretty sure it was effort to neon optimized Opus. And do you have any idea the Lex libraries we should focus on? Any suggestions? Okay, I guess here. I'm sorry. Is here most of you are from the compiler team? Any from the develop? Okay. So thank you very much. And now comes to Q&A. Any more questions about the whole Neon optimization? Or do you want, do you have any suggestions on this?
How does the library, Ne10 library release flow work? Like, is it like a main, does it have a quarterly main release, or how does it, what is your release pattern usually?
I'm sorry, can you?
No, is there like a major release version and a minor release version? What is the timeline for Ne10 normally?
You mean major release version?
Like, is there, if
You mean the torchain? Or
no, for the Ne10 library.
Oh, for the Ne10, the release. Well, we have.
I think we have release versions. Yes, we have.
So there's no regular release plan so far. No regular release plan so far. We just release according to the specific features requested by the partners. For example, Opus, Google, WebRTC.
Yes, it's just when we add a new feature that we release the code as soon as possible, so there is no regular releases planned.
So in the end, did you settle on using Neon intrinsics, or did you use the C code with vector types?
You mean in the end in Ne10 or?
So the very final result. At some
This
point,
one.
you showed the C code, which we're using vectorized data types, but not Neon intrinsics.
I repeat your question to see if I understand. You mean in this
In this
case?
project?
In this
No, several slides before that, when you showed the C code of FFT loop. Yeah, that one. No, yeah, before that. So
this one.
yeah, so that is not using. That's not the final code. This is using normal multiplications.
Yes.
Yeah. So and then you converted that into using Neon
Yes.
intrinsics. Okay.
You know, Ne10 has support for ARM v7, and not all chip on ARM v7 has a Neon. So we have to provide some C code that does not using Neon at all. And so we have this code, and we have this snippet. So you mean auto-vectorize? It is a good point. We haven't never tried auto-vectorize before. I'm sorry. Can the guys from compiler help me that? Can we really auto-vectorize this code, this piece?
Most likely, auto-vectorization could happen. The result of whether it will produce good code is an open question. In current versions. In future versions, code will be good from auto-vectorization.
Because you still have to think about your data layout, right? So your loop size.
I guess there should be a benchmark for this authorization, right? Auto-vectorization. Is there a benchmark you are using, and so that we can check the status?
Not ready to discuss that yet.
Not really. Not ready to discuss.
Not ready. Maybe at next Connect. So vectorization is work in progress. Specific benchmarks, no, yet.
Oh, I see. I see. So that's all. Any? I'll ask again. Any input about less libraries? Then that's all.